Hello? Are we live? Can you guys speak in the chat so that I'm sure that you're hearing me okay? Okay, João is here. I know that. I can see you. But is everybody listening okay? So, Matt, I see Matt, Ashutosh, Bruno, Navid, Pedro Fazenda, Michael. Yes, so we are live. Everybody, thank you for coming. My name is Pedro Prats. I'm a product advisor, and I'll just be making sure that this expert session goes smooth today. In this expert session, we have João Ascensão, who has been a speaker in a few Landing.Jobs sponsored events, and he has always delivered. So expectations are very high today. João has worked for unicorn companies like Feedzai, Farfetch, Uniplaces. He's very much into detection techniques, machine learning strategies, machine learning operations, responsible AI, among other things. And I do reckon that today João is going to detail what goes into AI-driven applications. I'm looking forward to that. And I'd love this to be interactive. So, guys, please use the chat, talk to each other. Let us know if you're hearing us okay. If there's some hiccup, there's no problem. This is a group of friends here listening to what João has to say and to interact with him. You can ask questions. There's an ask a questions somewhere in your interface. You'll find that, and you can ask questions there. You can also ask questions in the chat. No problem. I'll be paying attention. João, the stage is yours. Go ahead.
Thank you, Pedro. Thank you for the intro. Welcome, everyone. I will share my screen, and please confirm you can see a presentation. Okay. Okay, I will assume that you can. Okay, perfect. So, hello, everyone. I will start the slideshow. And the purpose of the talk initially was to talk about how to build AI applications. But as many of you are probably aware of, this is an area that is still developing, and there is no such a thing as a canonical stack or a proper way to build AI applications. So we will have and we will try a different approach today. So let me just confirm something because I cannot. Okay, sorry, I just wanted to make sure that everything was okay with the chat. It is, you know the topic, we are ready. Now I will share my screen for you. Okay, here we go. This will be the agenda for today, and hopefully the presentation will not be too long. We will start with, we will define what we mean by AI applications. That will be the first thing. I don't expect that to be very long. And then we will explore 5 common failure modes in AI applications. So the approach today will be slightly different. We will invert the problem. So initially, our goal was to understand how to build AI applications, but many times, the most important thing is to understand what are the outcomes that we don't want, how to get there, and avoid that at all costs. Okay, so we will invert the problem and we will understand what are the most common pitfalls in AI applications, and we will understand how can we get in such trouble, and that hopefully by the end of the talk we all know how to avoid such problems. And the failure modes I selected for today are: first one, run against the wall of production; fail silently; lack of fault tolerance; focus on aggregate metrics and the generate feedback loops. We will detail, I know that they are not incredibly informative at this stage, this is on purpose, and we will detail what we mean by these failure modes as we go through the presentation. We start by defining AI applications. Imagine that we have an application. For now, we don't know exactly what we mean by application, but apparently there is an input and there is an output. And this input and this output are represented by the incoming arrow on the left and the outgoing arrow on the right. Typically, when we think about applications, applications are comprised of software blocks. Think about an application comprised of multiple microservices, for example. And when we think about these traditional software blocks, and I mean traditional not in the sense of being old or deprecate or anything like that, I mean traditional just in the sense of comparing these with AI components and AI software so that we can understand the difference later on. So how to reason about these software components? Well, we have a program that someone wrote by hand manually, the programmer, a set of instructions, and the program receives the input, runs the set of predefined, pre-written, pre-established commands, and will produce an output. And the interaction of the programmer and the goal of the programmer is to write the best program possible. And he has the ability to write the program and fully manipulate the program. Okay, he commands what to write, what not to write, what are the instructions, the order of the instructions, and so on and so forth. This also means that the programmer has full visibility on what exactly is in that program. For that, maybe he was the responsible for writing the program, but even if that is not the case, he can simply read the program and go through the program, go through the instructions, and really understand what's going on. Okay, and typically this is the standard flow of a software program. And you can write tests based on what are the expected outputs for this particular inputs and things like that, okay? And then you understand if the output that you are generating for a variety of inputs is the desired output. And if not, you can always go back and you can always change the program to make sure that you have the desired outputs. When we talk about AI applications, the fun thing about AI applications is that there is, maybe you have a bunch of microservices there, and you have a lot of incredibly important software components that are not AI based, but you have at least one component. We can think about one service, for example. We have at least one service that is learnable. And being learnable is very different from being explicitly programmed. Again, what do we mean by learnable? So we are going layer by layer, right? We understand an app. We know that an app is comprised of different software programs. And now we are talking about the AI application, and we understand that there is at least one component here that is learnable. And what exactly do we mean by that? Interestingly enough, you already have a learner. The one thing you have from the beginning, you have two things. You have the inputs and you have the outputs. And this is quite different, right? Because when we think about traditional programming, what we have inputs, maybe some of them even synthetic for our test cases, and we write the program, we run the program, and then we get to see the outputs and we get to validate the outputs. Here, things are completely different. In the case of, and this is an instance of what we call supervised learning. Supervised learning is when we have access to this output. Okay, we know, we have examples of, okay, for this input, this is the desired output, and for this input, this is the desired output, and so on and so forth. I know what the target output should be for that particular input. And for when we have under such a scenario, we have supervised learning scenario. And what we use is a learner. And the learner is simply the program is not, I will not write the program by hand. I will employ a learner, an algorithm that will learn the relationships between input and output and will write the program. So I never get to explicitly write the program. I never get to explicitly write the rules. I simply, the code that I write, and when you look at the code file, what you will find is a set of instructions. This is the learner that I want to use. Maybe it is a random forest. I want to run these transformations beforehand. And based on this learner, I want to learn a program to perfectly generate, the perfect output for this input. And this is quite different, right? Because what we are saying here is that we have at least one component in our application that was not explicitly programmed. The code that I wrote was to code the learner, and that code, the responsibility of that code, was to learn the mapping from input to output and to output a program with the ability to encode such a mapping and to generate such transformations. The final point about AI applications that I want to make is that we already know from the previous slide that we will learn the program from data. We have inputs, we have outputs, we have the learner. They go through the learner and this will generate the program. And therefore, this will generate two different moments or two different pipelines that we need to consider at all times. The first step for this AI component is to train the model. I have some training data, the labeled examples, right, with the input and the output. I have this training data, and I will learn the model based on this training data. So I will learn the program, and the program here is represented by the blue box called model, okay? And then I will need to deploy this, and I will need to incorporate this in a service to use this program, right? So think about the model as being a static asset, for example. It is a set of rules encoded in a certain way with a certain format or a set of parameters, and it is like any other static asset. And you will need to imagine that you want to build a custom service. For that, you need to build a custom service. You have to load the model. You need to build all the necessary infrastructure. Imagine that we are building a REST API. You need to build the REST API. Everything is like any other service, but you will use, instead of using code that is explicitly written maybe inside the service, what you will have is the model, right? You will load the model and you will load the model. So you can think about this serving as being sort of almost like a container or a packaging of the model where you have everything that you need to have a complete service, but the model inside was not explicitly programmed. It was trained based on training data, and then it was somehow sent and loaded by this service to make predictions. Very importantly, the two notions that I want you to retain from this part is that we have at least one learnable component. The learnable component was not written by anyone. It was learned based on a set of inputs and outputs, a set of labeled examples, okay? And this learner generates the program, and no one explicitly writes this program, okay? Then, once we need to have a service using this program, right, we need to take the program that we trained and we need to load that into an application, and based on that, and then use that to make predictions on inference data. One important note here is that this inference data, you don't need to be, it doesn't need to be real time, or it doesn't need to be streaming. Many times you train a model offline and then you deploy the model to make predictions on, to make real time predictions, but you can also make batch predictions, or you can have a certain part of your system, maybe the feature engineering will be done. Some of it will be real time, some of it will be batch. So it doesn't need to be real time. The most important definition that I want you to retain at this point, and the most important notion that I want you to retain at this point, is that we have two moments. We have one moment of training and we have one moment of inference. And this is quite different, right? And when we have good or bad results, the good or the bad results when serving predictions, you need to trace that back. Either the problem can be in your serving, but the problem can be with the model, the problem can be with the data. So you need to be aware of all these different moments, and you need to keep the two pipelines in your mind at all times. With that being said, I will do a short break here, and I want to see some engagement in the chat. So far, so good. Are there questions? So this is a good. I think this is a good moment for us to maybe take a break and discuss a little bit in if that's the case.
Oh, I'm good so far. I don't see any questions, guys. If you want, you can ask questions in the chat. You can also ask questions via the Ask a Question button there. There's polls for you to answer.
Okay, then I will move on, but it will be at your risk. Okay, so audience, if you have questions, if you want to engage, if something it's not clear, let me know, and I am here to address any questions that you may have. Okay, I really like questions, and this is a new presentation, so you have the honor of seeing a fresh presentation, but there are also problems with fresh presentations. If you find some, let me know. Okay, thank you. So let's move on to the interesting part. Okay. The first thing I want to explain is the methodology that we will be using today, because methodology is also important. So I told you that instead of being very explicit about how to build AI applications, I will be very explicit on things you want to avoid when building AI applications. So where does the idea, what is the source of the idea? So one quote that I really like is from Charlie Munger from Berkshire Hathaway. And the quote goes as follows: "All I want to know is where I am going to die, so I will never go there." And this is powerful, right? Because it's very hard for us to say what is the exact right thing to do at any exact moment, but there are certain things that we know for sure we want to avoid. Death is probably one of them. So certainly, if I know where I am going to die or to fail or whatever, I certainly want to know that so that I can avoid that for sure. So this is one of the inspirations. Okay. Another inspiration is what Nassim Taleb calls the via negativa. So, and in action, the definition goes as follows. In action, it is a recipe for what to avoid, what not to do, subtraction, not addition. And this is very important, right? Because many times the most difficult thing is to subtract the things that not only don't add value, but are actually undermining our effort, right? So understanding what are these things that are bad for us and subtracting that can be a very impactful thing to do. And again, it's very hard to say what is the one thing that we need to do or to add or etc. But many times it is very hard to see and to grasp what are the things that don't add value and that create problems. And that is a more objective thing to discuss. And finally, from Naval Ravikant, we have a similar idea. I don't believe I have the ability to say what is going to work. Rather, I try to eliminate what's not going to work. And based on my experience working with teams to build products at Uniplaces and Farfetch and Feedzai, I am very fortunate I failed many times basically. And knowing that I think this is a very rich experience that I can share with you, because I can share with you many things that you really don't want to do when building AI applications. And I will try to leverage that experience, and I will try to leverage those failures to give you a roadmap of things to avoid. And I really believe that is a very valuable thing. First and foremost, I want to explain you this diagram, okay? Because we will be referring and we will be using this diagram quite a lot. And I want to make sure that we all understand what is going on here. So this is a very, very simplified diagram of an AI application, okay? And what do we see? The first thing that we see is that we have the two pipelines here. We have a training pipeline and we have an inference pipeline. In the training pipeline, we train a model. In the inference pipeline, we serve a model. We serve the program that we learned, and we use it to make predictions on previously unseen data. So at the top, we have the inference pipeline. At the bottom, we have the training pipeline. Now, from left to right, the first, on the left, we have two databases, okay? They represent the training data, the data that we use to train the model at the bottom. And at the top, we represent the inference data. So the data that we will be making predictions for, okay? And this is the raw data, okay? This is how we receive the data. This is the data that we received for training, and this is the data that we received to make predictions, okay? No changes whatsoever were made. And this is the first step, the input of our system. Then we have a block called feature engineering. Feature engineering is when we, based on the raw data, we do transformations and we perform computations and we generate new attributes that will be relevant for our model. One example of something that we use frequently at FeedSci is, imagine that I have a table in my training data with a lot of transactions. Each row represents a transaction. Okay. And these transactions, they belong to cards. Okay. So I can have multiple transactions for each card, but each row is a transaction. Imagine that, but maybe certain things that could be informative. Imagine that for each transaction, I will enrich the data that I have with what was the amount spent by this particular card in the last 24 hours, so that I can have a sense of the consumption pattern of that particular card. Or typically, what is the time difference between transactions for this particular card? And what is the time difference from this transaction to the previous transaction done with the same card, right? These are computations I can do that will create additional value and that will convey additional information to my model. And this is what we mean by feature engineering, okay? Very high level. I don't want to zoom in any particular details today. Our goal today is mostly to have a higher level picture. Once I have all the raw data that I need and all the features that I need, I will train my model. I will use the learner to output the program, to learn that program, to learn that set of instructions, to learn what is the output for that particular input, okay? Learn that mapping. The second step, so we have the raw data, we are inside the modeling stage. We already went through feature engineering, model training at the bottom, and now we will see offline evaluation at the bottom. Imagine that I use different learners, for example, to learn different programs. I need to select what is the program that has the best results, okay? And this is the first purpose of the offline evaluation, to know what is the best program that I generated based on a set of candidate programs. Another very important thing is that typically you train the model with a certain part of your training data, and then you want to know, okay, this is how good my model is on my training data. But truly, what we will be doing when serving predictions is making predictions on previously unseen data. Okay, so you also want to evaluate how good your model is making predictions on data that is previously unseen, and you want to do this to try to understand, okay, when I go live, what is the expected error? We will not go into techniques to do this. I really don't want to zoom in. I just want you to understand that we have two very important goals here with the offline evaluation: model selection and understanding how good my model should be, what is the expected performance of my model once I go live. And this is what I want to do with my offline evaluation. If the model is good enough, I take the best possible model and I will include that in the case that is the service that I built for it to make predictions, and I will make predictions. This is what we mean by serving at the top. Okay, when we see we have the model as a 3D box, and then we have the arrow going up and we have serving, and this is where we serve the predictions. Once we are serving the predictions, it is very important to evaluate the quality of these predictions. And we do that because typically, eventually, we will have ground truth. Many times, the ground truth is not immediate. Imagine that we are labeling incoming transactions as being fraudulent or legitimate. Okay. We are doing that. Maybe we don't have access to the ground truth, but eventually, if a fraudulent transaction is not blocked, the client will contact the bank, right? And he will request that a refund for the money because he was not the one responsible for the transaction. And once that happens, we will have access to the ground truth. We will know for sure that that transaction was not legitimate. Okay, and this is why we have labels connected to online evaluation and serving as well, because we need access to our prediction and we need access to what the ground truth is so that I can evaluate predictions against the ground truth to understand whether I am doing a good job at making predictions or if my predictions are absolutely terrible, okay, or somewhere in between. Hopefully the diagram is clear, and now we will move on to the first failure mode. And the first failure mode is running against the wall of production. What do we mean by running against the wall of production? We deploy the model, and the online results are quite different from the offline results. So when we did the offline evaluation, we were expecting a model to be absolutely excellent on all examples, and then we go live and the model is absolutely brutally wrong in 80% of the examples. And this is quite unexpected because we were expecting good results. Probably we communicated internally that what were the results that we were expecting for the model, maybe even externally. The product team was expecting a certain standard of performance to be able to support the features that rely on this model, and then the performance is absolutely terrible. This is quite common. Okay, this is not something that happens once in a while, and it happened to me more than once, actually. So this is the outcome that we really don't want, right? This is a terrible outcome. Okay, so I hopefully we all agree that we don't want to go there. This is the first step of the inversion approach that we are taking. So how do we get there so we can never take that road ever? Okay. The most classical example is faulty evaluation. Okay, so you were not evaluating your model properly. And since you were not evaluating your model properly, your estimates for performance were completely wrong, and then you are performing way worse than expected on unseen out of sample data. This is something that we don't do on purpose, right? Even when I did similar mistakes in the past, it is not on purpose, but maybe there are certain temporal effects in your data that you are not accounting for when doing your validation strategy. Your validation strategy doesn't account for time, and therefore your results and your validation strategy will not be very good. Or you use all your data for training and you don't have data for tests and to calculate the generalization error. So regardless of the particular error or the particular technique that you want to use, really think clearly and define clearly your offline evaluation strategy. This is critically important. Okay, and typically this is the source of the problem. So if you want to have very different results, one thing that you can do is you can have a terrible evaluation strategy, or you can disregard your experimental setup and your offline evaluation. But if you don't want that, this is a good road to avoid. Another very common thing is the training serving skew. So you trained with a certain training data and your production data is completely different from your training data. This is again something that you don't do on purpose. And I will give you an example. Think about uni places, for example. And imagine the hypothetical, obviously, case that we were using photos to extract certain characteristics of the room. So imagine that we use the photo to understand if the light is proper, if the furniture is modern or not, things like that. Imagine that we are doing that. And imagine that we train that model with images from Airbnb. So just using professional photos, okay? And our model is absolutely incredible at extracting all these different things from the professional photos. And then you have a service, and then you deploy the service, and you tell your amateur photographs to, okay, go to the room, take a picture with your mobile phone, upload to our service, and we will be able to extract all the relevant features. Your training data was based on photos that were absolutely perfect, professional photos, perfect lighting, and so on. And what you are now receiving to make inference on are terrible photos, out of focus, shady in every. So this is not about. So I am exaggerating to make a point. Okay, but the point is, mobile phone pictures are very, very different from professional. Mobile phone photos are very different from professional photos. And if you train on professional photos and you have a really good model on professional photos, and then you want to do inference on mobile phone photos, the results will be terrible. There is simply no way around that. So if you want to have very different results, a thing that you should do absolutely is have training data as different as possible from your inference data. If you don't want that, make sure that the training data that you have is closely related to the task that you will be trying to solve online. So here we can see in the raw data column, we can see that there is a problem with inference data and or training data. In short, they are quite different. And we go full force against the wall of production. Another way to accelerate towards the wall of production is pipeline inconsistencies. Many times what we do is imagine that you have a team of data scientists working in Python, and they do the feature engineering, and they do the model training, and they do the offline evaluation, and they have a perfect model. And they deliver the model to an engineering team. But the engineering team works, and the application is a Java application, and they need to rewrite everything in Java. And not only will they need to use the model, maybe that part is the easiest part, but all the transformations that are required so that the model, so that the data, the raw data, is ready for the model, they will need to implement that in Java. Okay, so that the model will receive data in the exact format that it is expecting. And the potential for problems is immense, right? Because you will have Java developers copying transformations from Python code, making sure that the transformations are exactly the same. Again, this is an example, exaggerated example to make a point, but you are rewriting all this code, and in all probability, the transformations will not be perfectly alike. And if the transformations are not perfectly alike, then the data that will reach your model is not like the model, the data that you use to train the model. And we are back at stage one. Data is different. The predictions will be absolutely rubbish. Okay, so this is something that happens quite frequently, and it's when you have discrepancies between how the data is handled in training and how the data is handled in inference. Okay, this is also quite common. And keep in mind that we will be doing a poll afterwards to try to understand what is your favorite or what is the most common failure mode based on your experience. Obviously, this is all quite new and based on my experience. So I will be very, very curious to know your opinion. So go ahead, Pedro.
João, we have here a question from Alexandre. He's asking if we should split the sample in three: train, test, and validation.
Alexandre, so let's go back. Let's go here. So that is a very good question. My first and foremost, yes, you should split. You should also understand very clearly if you have temporal effects. Imagine that you have time series data. You also want to make sure that you train in the past and you test in the future to avoid information from the future leaking into your training and compromising your experimental setup. So this is okay, but if you have temporal effects, for example, you need to take extra precautions. And my bigger point is think clearly and articulate your validation strategy, research your validation strategy, and make sure that your validation strategy, there are a number, split in tree, k-fold cross-validation, stratified. So there are different strategies that you can use, but think clearly and give it a lot of thought, okay? Because if you have a bad offline evaluation strategy, that is a small thing that is absolutely certain to compromise the entire project. Does it make sense?
Good. Alexandre, if you're not happy, you can ask again. Okay.
Bother me, Alexander. Go ahead. I will move on, but if you have more questions, and Pedro, feel free to interrupt at any time. That is okay.
Good.
So pipeline inconsistencies, yes, they happen and they are quite common. And many times you do have to duplicate some transformations and to duplicate some code. And you really need to make sure that the output is consistent between your pipelines. Your feature engineering in inference is exactly like your feature engineering in training, else your model predictions will be absolutely terrible. We move on to the second failure mode. And the second failure mode is very common. And most of us practitioners are probably guilty of it at a certain point. And this is the silent failure or the Schrodinger's model. It's the Schrodinger's model because many times we do the offline validation. Then we have a model making predictions live. But if we don't take measurements on the quality of the predictions, is the model either good and bad at the same time? Or so what do we expect really if we don't measure the performance? So we don't want to open the box, right? And this is very common. And again, it's not something we do on purpose, right? This is really hard. And it's hard because two things. The first thing is once we deploy a model, we need to do the online evaluation to see if the online results match the offline results, right? To understand whether either we were able to go through the wall of production or we went full force against the wall of production. So we need to do that. And another very important thing is that the data flow changes over time. So your inference data, it's non-stationary. This means that, for example, imagine that you are scoring transactions. Maybe you have a certain pattern of transactions during the Christmas season, and you have a different pattern in summer. Okay, this is seasonality. This is to be expected. The data will not be stationary. But more importantly, you have all sorts of variations. For example, in fraud, once you deploy a new model to block financial crime, you will have professional criminals adjusting the strategies, trying to bypass the model, trying to understand. So they actively change the attacks, they actively change the behavior, and they actively change the data. So the transactions that you see now are very different in the patterns that are there, are very different from the transactions that your model has seen in training. And because of that, you have to continuously evaluate the performance of your model live to understand whether there is degradation or not. This type of silent failure is very common. One thing I want you to understand is that what do we mean by silent failure? Imagine that you have a problem with a service that you deploy, right? You have errors, you have logs, and you have traces, and you have all sorts of information. So if there is a problem with the service, right, the service will go down, or you will have errors, or the logs will be weird, and you can use the traces and so on and so forth. And typically, when we think about monitoring, we think about these things. But an AI model is entirely, an AI application is entirely different. All of this is still relevant to your AI application, but ultimately, the quality of your AI application will be defined by the quality of the predictions. And the quality of the predictions, it's not something you will catch with your stack traces and with your logs and so on and so forth. Simply, it is not, because if you are doing bad predictions, you are still making predictions. So from the standpoint of your software, everything is great. Everything is absolutely great. Data comes in, goes through the service, predictions go out. Everything is absolutely perfect, except it is not, right? It is not, because there is something you are not seeing, and the something that you are not seeing is the online quality of your predictions. Okay. When you have this type of issue, silent failure will prevent the timely detection of problems. Okay, you don't know that the performance is degrading over time, and will also undermine the resolution of issues, because if you don't know there is a problem with your application, obviously there is nothing to solve, right? And this is absolutely certain to lead to failure as well. So again, how do we get there so that we can avoid the trap? AI applications are quite different in the sense that you need to build your monitoring explicitly, and monitoring is a first-class citizen of any AI application. And it's not software monitoring, it's monitoring the quality of your data and monitoring the quality of your predictions. You always need to do that, okay? This is a very important lesson. You need to know whether your data is changing over time, okay? If, for example, the transactions that you see today are entirely different, or imagine the example with the photos from Uniplaces, okay? You need to know, okay, these photos are entirely different from the photos that I used in training. Photos are, the quality of the photos is degrading tremendously, okay? You need to know that. And you also need to know what is the impact on your online evaluation. And typically, what we want to do is we want to track and measure and log metrics that are specific to the performance of your model. This is very important, okay? And typically, the three things that you want to measure are covariate shifts in your data that maybe maybe your data changes, but your online evaluation does not change much because the data is different, but the patterns are mostly the same. Okay, you have, it's Christmas, transactions actually are quite different, but the fraud patterns actually are the same, and the features of a fraudulent transaction are about the same. So the data is quite different, but it's not impacting my model. Or you have label shift, where actually the distribution of the labels is changing quite a lot. Maybe it is Black Friday, and I am receiving a lot of fraudulent labels, and I am receiving a lot of fraudulent reports. So I have way more fraudulent reports than normal. But maybe my model is performing just okay. It's the same fraud patterns that my model already is aware of, just more frequently. Or maybe you have concept drift, and maybe the patterns are really changing, and your model is looking for certain types of patterns, and those patterns are meaningless now, and you need to learn different patterns, and you have a big problem in your hands. All the three are big problems, by the way, but they are quite different things. So explicitly build for monitoring. If you want to fail, a good idea is to don't open the box. Okay, don't open the box. Don't build the monitoring. That would work brilliantly. But monitoring is not all you need. What you truly need is true observability. And observability is from the monitoring that I have, from the state that I can see, from all the measurements that I can see, can I investigate? Can I perform attribution of problems and understand where the problem is? Is it an inference problem or a training problem? Is it related to my service or to my model training? Is it the feature engineering? Therefore, true observability is being able to, from the observed measurements, reverse engineering all the states of my AI application to be able to understand what exactly is going wrong. Okay, and monitoring is all about the time to detecting a problem, and observability is all about how fast can you go about solving a problem with your AI application? Because you understand the root cause and you solve the root cause. Again, if you want to fail, ignore observability at all costs. A particular kind of hell is cascading failures, because many times one thing you have, for example, in speech recognition, a good example is the example with the Uniplaces photos. We were not using the photos in a nutshell, right? We were using the photos to then compute a scoring to see what were the most desirable apartments. So we have one model extracting information from the photos, and that model then is used as an input to another model that computes the score. This is a very special kind of help. Really, really, really. This is when you chain AI models together, and when one model changes, right? Imagine that the labels are changing, or the patterns are changing, or you retrain the model. When one model changes, the data changes, right? So the things that he will be sending to the model that is downstream are different, and the model will be, okay, this is entirely new data. I cannot perform on this new data. The interesting thing is that this new data is being generated by another model, so everything is entangled. When you change a small thing in either, imagine you have two models, each one with the two pipelines, and you change something there, right? You need to change, that will change everything, right? And this is a very special type of hell. And many times and more, we see models working together to achieve a certain goal. Maybe you have one model doing speech to text, and then you are doing topic modeling on top of that text. Or you are extracting information from photos, and then you are doing classification. Or you are observing something about behavior, and then that behavior will inform your fraud model. Once you connect the models together, everything that we are saying about models holds true, except that they are also connected together. So it's a very, very special kind of help. One quote that I really like as well is, machine learning is really, really good at partially solving just about any problem. Okay. What do we mean by this? And this is a quote, by the way, by Chris Dixon from Andreessen Horowitz and eBay, and he is a famous investor. And the one thing that is important is AI is absolutely great at solving about 80% of any problem. The other 20%, what we call taming the tail, the long tail, the other 20% are really, really hard and really, really expensive. Because these 20% will be rare events that are very unlikely, for example, to be present in your training data. And if you want them to be present in your training data, you need to collect data for a long period of time to be able to collect all these rare events and rare instances. And imagine you are collecting the data, they are rare. So basically over time, you are mostly accumulating data that encodes patterns that your model is already know, waiting for data that encodes different patterns to come every now and then. So your cloud bill is tremendous as well. Okay. So it's not really, really hard to get this 20%. They are also quite expensive. Okay. And this is a simple observation with very interesting corollaries. At least to me, there are very interesting things to me. If this is true, many times we think about AI, we think about the competitive advantage being in the model. And to me personally, that is not the case. If you have a model that is good enough, that model will probably get you to the 80%. Random forest or light GBM or deep learning, if we are thinking about tabular data, of course, they will work, okay? And you will eventually achieve these 80%. And all of these models, they are out in the open, right? You don't need to investigate new models or architectures to get to these 80%. If you want to get the extra 20%, yes, maybe you need new models, you need more data, you need all of these things, but this is very expensive and this is very time consuming, okay? And being super honest, getting all the possible edge cases representing in your training data or your model or with rules that complement your model, being able to capture all of these, it's not feasible. It will not happen. You will not get to the 100%. And you must assume that. So the first corollary is that, one, model is probably not your competitive advantage, but the most important corollary is that your AI needs to be fault tolerant because it will fail. It's the nature of the game. Okay. And when you don't recognize that, that leads to AI applications that are not fault tolerant and cannot withstand high stakes domains like health, like finance, where it's really, really important that you either have excellent performance, and when you see an edge case, you need to be able to deal with that in a graceful manner. Okay. And if you don't recognize these, if you simply deploy your model, okay, and you don't recognize that your model will eventually fail for certain, okay, if you don't do that, you erode the trust of the people using the system. And they will stop using the system and certain death yet again. So how do we get there? One important thing is lack of human oversight. Okay. If your model is not sure, make sure that you have a human in the loop that can complement the model. If your model is not sure, ask for a human review. Collaborate with a human person to make sure that you have the proper decision. Okay. This is very important. Not only that, not only the human in the loop, but also make sure that human operators, data scientists, your engineering team, your product managers, and so on and so forth, make sure that everyone has access to the necessary information to evaluate the model, to see how the model is performing in certain cases and whatnot, so that you can continuously adjust the system to make it more and more fault tolerant. Okay, this is incredibly important. Again, your model will fail. Assume that. Okay. Another important thing is that if you know that your product will fail, build a product that is fault tolerant by design. If your UX, if your UI is not fault tolerant, if you create the expectation in your end user that predictions will be perfect, once you fail one time and you lose that trust, right? So you want to protect from that. So instead of showing one recommendation, oh, look, this is a good film that you should watch, provide 10, provide 20, provide as many recommendations as you need to have good confidence that you are robust enough to edge cases. When you search for something in your Google search, and Google is amazing, they don't provide one result, right? Google search is probably a brilliant and an early example of brilliant fault tolerance in AI. They don't show one result, they show a bunch of results. And they even provide ways to override the results with ads and so on and so forth. They understand this. They understand that it's a problem that they cannot solve. You ask one question and they will give you the link, the exact link that you are looking for with one result. They know that there will be edge cases and there will be certain situations where they will be absolutely unable to solve this. So they don't try. They have a UX and a UI that is fault tolerant by design. Are there questions?
So far, we have a generic question from Ayula. I hope I didn't butcher your name. Sorry if I did. This is the classic question about cloud services versus open source tools. Cloud AI services on frameworks versus open source tools. What do you think about that?
We can talk about that after the presentation in more detail, but my answer is always more or less the same. So even when we use open source tools, many times we are using that on Google Cloud or AWS or Azure, right? So their business model is very solid in terms of they focus on providing the infrastructure and the computational power and the databases and the storage that you need to store all of this data. So yes, even if you use open source tools, it's very hard to decouple that from. You will need, in all probability today, you will need cloud resources as well. Then, if you use the solutions that they provide that are more intuitive, or whether you prefer open source tools, I think it all depends on the control and the complexity of the task. If you want to control a lot, and if the task is very specific, probably you want to have something more specific and use open source tools. If not, probably it is perfectly fine to use AI services from them. This is really an opinion, okay? It's not a very, so I always like to give my confidence level. My confidence level is about 60 to 70%, okay? So it's not my main area of expertise. So this is more of an opinion.
So far, we're
Here,
good.
okay, I defer to another human in the loop for that. Another very important thing is, if we know that it is very hard to solve every single edge case, if we have a task that is enormous, this is nuts, right? Because imagine that one thing is my task is to know whether this particular place room is of interest to you and if you want to book this room, or I want to know very specifically what is the topic of this customer support ticket. And maybe this is even broad enough. Maybe I want to identify tickets that are related to returns. Okay. When we were approaching topic modeling in Farfetch, we didn't try to solve every single typology at once. No, we maybe we start with delivery, and because this is the most important. And do we have good results for deliveries? Yes, we have. Now we go to returns. So narrow your task, and this is what we call the minimum viable task. And the minimum viable task is as narrow as possible. You want a task that is very narrow and still delivers value. You want to understand what is the narrowest task that you can solve that will deliver value to your user, so that you can reduce to the maximum the data complexity, and so that you can reduce to the maximum this problem with the edge cases. Okay, imagine that you have edge cases not in a single. If you have a very broad test, you have all sorts of edge cases and all sorts of problems, and maybe you have edge cases related to returns and edge cases related to deliveries, and all of these accumulates, right? So if you want to be fault tolerant, and even the mechanisms that you build to provide fault tolerance for a certain task, if you have a very broad task, it's not immediate. What mechanisms can you build for that, or what kind of analysts can you include in the loop with the right expertise to help out the model? So minimum viable task, I think this is one of the things that we talk the least in our community, and probably one of the most important things. Minimum viable task, what is the narrowest possible task that we can solve and still deliver value to our user? And as we approach the end of the presentation, these two last failure modes are more are shorter, I think, and more to the point. Focus on aggregate metrics. This is also very common, and it goes a little bit like this. My model is absolutely great when I see the performance of my model in all data, all inference data, and the performance is great. So I don't worry. But maybe the performance overall at the top level is good, but when you go to specific groups and specific regions of your feature space, maybe for certain users your predictions are great, and for certain users your predictions are terrible. And eventually you will churn those users, and maybe those users are super important to you. All users are super important, but maybe you are losing even critical users, and you don't know why. And the reason for that is that you are focusing on aggregate metrics, and aggregate metrics really don't work for AI. You want to make sure that not only you have a good top level performance, but you have a good performance across the feature space and for all the subgroups that matter. This is really bad. So how do I get there so that I can avoid that path? Use course level metrics. Okay. Don't define slices. If you don't want to go there, one thing you can do is define slices a priori. So for example, I want to evaluate for sensitive groups. I want to know exactly what is the performance of my model for people of a certain gender, for people of a certain race, for people in a certain region, for people with a certain job, for people. I want to evaluate separately for all of these. And I want to make sure that my performance is good enough for all of these. And if my performance overall is good, but I fail terribly for one of these groups, I can do one of two things. I can either don't deploy the model, Or I can use fault tolerance, right? I can create rules that will improve the performance for that specific group, or I will include a human in the loop for that specific group. I will wait until my model has good results for that specific group, and while I wait for that, there will be a human making the decisions or assisting the decisions. I can use fault tolerant design, but for that, I need to be aware that my performance is non-uniform. And many times this is something that is not considered, right? But I can also do this auditing a posteriori, meaning that imagine that I have a good performance and there are techniques that I can use to see, okay, let me create random groups, for example, inside my data, and let me see if the performance is very different for each one of these groups. I want to get a sense of variability. I want to get a sense of is my performance uniform across the feature space or not, right? And maybe if I am underperforming a certain service level for a certain region, maybe I want to employ a different strategy there. If I don't, all hell can break loose. Compliance problems, ethical problems, business problems. Imagine that you are failing in a very important geography, for example, and really, really terrible things can happen. One example provided in learning materials by Google is imagine that you are training a model. So to give a different example too, imagine that you are training a model to predict whether a certain person has breast cancer or not. And imagine that in your training data, there are no men. Your model will not be able to predict if a man has breast cancer or not. It will not be possible, right? And knowing that, and this is an example that is less contentious, but all the examples count, right? If you are training a model to exclude or to select what job applications go forward, and if you know that typically there are certain groups like women and so on that typically when you look at the labels, there is a systemic bias there, okay? And if your model is absolutely terrible there, you want to know that and you want to be responsible about that. But it's not only the one thing I want to convey is that fairness is important here, but this is a higher level failure mode, okay? Maybe I am simply failing in a random subset of my feature space, okay? The big problem here is that the performance of the model looks good, but for certain subgroups, the performance is not good at all. And this is enough to make the product fail. Okay? And fairness is a special subcase of this bigger case of your model being very good for certain types of data and very bad for other types of data. And finally, the last one
João,
is go ahead.
I'm sorry, João. Can I interrupt you now?
Of course, of course, of course.
There's here a few two questions that are regarding aggregate metrics. One is from Alexandre. He's saying you are splitting based on key characteristics or even grouping them with, in example, k-means, or should be the business defining those groups?
I really like your questions, Alexander. Very good question. So typically what I mean is really using a key characteristic, and that key characteristic a priori, when we talk a priori, typically that characteristic can be a geography that you really care about. So for example, users from the UK, and that, for example, can be defined by the business. But if you have sensitive attributes like gender, race, you also want to include that for sure. Okay? So you also want to create those slices, and you also want to evaluate separately for each one of these sensitive groups. So this is also very important. And these are examples of slices that you can create a priori. A posteriori, there are certain things that you can do. So for example, you can do error analysis to understand what are the typical errors of your model, and you can try to see if there are patterns. Okay, maybe your model is not very good at recognizing dogs, and when you go one by one doing your error analysis and you go one by one seeing examples of failures by your model, you see, okay, this is a dog, this is also a dog again. Clearly, my so, and this one is not defined a priori. It's something that based on the results, you explore the results a little bit, you see where you are failing, and you start to understand whether there is a pattern and whether there is specific types of examples that you are misclassifying, for example.
Nice. I think you can go on. There's another question here, but I think we'll leave that to the end. It's more generic. Okay.
Okay, we are almost there. And this is the last one, and this is one that we see in the news and so on, but maybe it's not very well explained. I will do my best. Typically, the generate feedback loops, they happen, they are really terrible. And what they do is they create what we call filter bubbles, where you are recommended always the same type of content. You always consume that kind of content. So the next recommendation of the system will be even narrow inside the type of content that is already being recommended. And you will focus on that and narrow, and you are inside a bubble, right? And this is what we call the generate feedback loops, and we will define them in one or two slides. But they create filter bubbles. So a problem that they create is that the performance is terrible and they perpetuate bias, right? So you are not exposed to new things, or you are not exposed to things that. One curious thing about these loops, imagine that I want to provide you with one recommendation, and I have one article about skateboarding and I have one article about fatherhood. And the one about skateboarding has a 90% chance of being of your of being enjoyable to you, and the other one has 89% chance of being enjoyable. So we are talking about 1% of difference. So they are about the same. But I will recommend the skateboarding, and you will see the skateboarding and you will like the skateboarding. And the next time I run my model, maybe the difference is already 2% points, because I have another data point of you liking skateboarding. So I will recommend skateboarding again. And then maybe it becomes 3%, 4%, 5%. And after enough rounds of these, you only receive news and articles about skateboarding. And if you go all the way back, the difference in probability was 1%. Right? And this is the problem with the generate feedback loops, is that then you become obsessed with skateboarding, and all that matters in your life is skateboarding. But actually, before all of that, you really liked fatherhood as well, right? This is simplifying the example, but to make the point again. But I think it works, and the performance is not good, right? Because fatherhood was good for you, and the more you filter out, and the more you go about selecting the articles about skateboarding, probably after a while, I am tired of skateboarding. I really don't want more skateboarding, and the articles that are being recommended I are not even good skateboarding articles, and I am, what the hell? Why am I receiving terrible skateboarding articles when there are so many articles in the world? It's not very good. It's bad for bias. It's bad for performance, and it's bad for variety and serendipity. We all like to be surprised by AI systems. We want AI systems to show us things that we don't know or that we are not aware of. And many times when you have this kind of feedback loops over time, these degenerate and you lose control of that. And your system becomes not very useful and eventually fails, unless you are. Am I allowed to criticize Facebook or not? With just joking. But you see the point, right?
Please be my guest. If you want me to join, I'm all for it.
But I just want to, this is to make a point more so that you understand when we talk about these echo chambers, and when we talk, this is what we are talking about. And technically, how does it happen? So let's go back to skateboarding and fatherhood. The present output of your system will influence future outputs, because I recommended skateboarding, you read the skateboarding article, and that will reinforce the certainty of my model that you really like skateboarding articles, even though you also like other types of things. So I will, the fact that I recommended skateboarding to you led to you reading the article, and that led to me reinforcing my belief that you like articles about skateboarding. And this can be said about QAnon or whatever we want to call it, right? Any type of system that consists of what we call natural labels, and natural labels typically are it is what we call when the user is the one providing the label. So for example, when you click one article, you are providing the label to the system, saying that, okay, I really like this article, or I sort of like this article. If you read the article to the end, maybe you are providing the feedback that the article was very good. And with natural labels, many times you have this problem, right? And this leads to services that after a while people don't really enjoy using, and AI applications that not only have a lot of impacts in terms of ethics and fairness and so on, but also are not particularly good apps, or the recommendations after a while are not particularly relevant. And two, I have a bonus. So obviously you are already very tired, but I just want to give you a bonus. And the bonus is overarching to all of these. The worst thing you can do is try to solve the wrong problem. um,
Uh, João, João, I think you, João, not listening. João. I think João has some kind of problem. I hope it isn't the internet. You know, we've had a cyber attack here in Portugal to one of our main ISPs. Oh, but João is back.
yes, and I am using Vodafone.
Yes, that's what I was talking about. Perhaps it was the cyber attack.
Yeah.
So you can go on. Sorry, it was like just a few seconds.
Thank you. So I was telling you about the iron triangle of AI. So if you want to solve a problem that is very broad, then you will need a lot of data and you will need a lot of domain knowledge. And if you don't have one, or if you don't have the other, probably you will not be able to solve that problem with quality. The other part of the triangle is data, right? So how much data do you have? The quality of the data, is it good? Is it bad? Do you have labels? And the other one is domain knowledge. And if you want to know, is this a good problem for me to solve with AI? You always need to consider these three together. Imagine that you don't have a lot of data, for example. If you have a lot of domain knowledge, you can go around that, because you can have the human, you can have the fault tolerant system, you can have the human in the loop, you can create rules well curated that will complement your AI, and that will protect your AI from the edge cases while you collect more data. So if you don't have a lot of data, but you have a lot of domain expertise, you should be okay, for as long as your problem is not too broad. Because if your problem is too broad, then your domain expertise, maybe you are a domain expert in part of the problem, but as you become broader and broader, and as the problem becomes broader and broader, you are not an expert in certain areas, and you will not be able to make up for the lack of data by using your domain knowledge alone. So if you want to know whether this is a problem that you can solve with quality, again, this is an idea, okay? Again, uncertainty level very high. I just came up with this, okay? But based on my experience, these are the three things that you must consider. How broad is your problem? How much data do you have? How much domain knowledge do you have? And if you don't have a lot of data, then you better reduce your scope and you better have a lot of domain knowledge. If you don't have domain knowledge, you better have a lot of data so that your model can learn from a lot of examples. And if you don't have neither, you don't have a lot of data, you don't have a lot of domain knowledge, really, really start with a minimum, the minimum viable task. Identify your minimum viable task that you can solve and start from there. And over time, start enlarging your problem. And this is my last tip. So we need talent, we need your talent, we need your energy. Don't get stuck on trying to solve the wrong problem, please. Okay. Recap. We spoke of failure modes, how not to build AI systems. We talked about running against the wall of production, failing silently, or the Schrodinger's model, lack of fault tolerance to edge cases, focus on aggregate metrics that generate feedback loops. If you want to fail, I highly recommend picking one of these should be enough. If you don't want to, these provide endpoints that you want to avoid. And throughout the presentation, we also exemplify some of the paths that if you want to fail, you want to take. If you don't want to fail, you can avoid. I cannot give you a roadmap on how to succeed. I don't have that, unfortunately, but hopefully based on my experience and based on my own failures, you can learn from these and stay away from these roads and try to experiment different roads for you. And finally, don't get stuck on the wrong problem. That would be my final recommendation. Hopefully this was fun to you, and that was it.
Thank you, João. We are already over time, but there are a few questions here. So if you can, let's just stick around and answer those. Are you okay with that, João?
I am okay with that.
So there's another question from Alexandre. He's asking on the feedback loop, does a stratified sample, it resets and balances all your preferences, or any technique that solves this failure?
So very good question. If you are interested in this problem, the literature on this problem is really big, and it's really big because this is a very common problem in recommender systems. Let me give you the most simple solution. If the problem is getting stuck, you can include a little bit of randomness. Okay, every once in a while recommend something random, or instead of recommending the first option, recommend something a little bit more down the list or something like that. Insert some randomness so that you don't get stuck in a filter bubble. Okay, so injecting randomness is a wonderful thing. It's not the most clever strategy in the world, but typically it solves most problems, and this is not an exception. So randomness can help quite a lot in avoiding filter bubbles.
And there's a question here from Ayula. With the advancement of grid search and random search, is there still value in feature engineering?
Yes, feature engineering is tremendously important. It will not go away, and particularly because we don't have unlimited access to data. So we need to be able to extract as much value from data as we can. Feature engineering provides us with a way to use the expert knowledge. And if you think about the triangle, the iron triangle of AI, if you don't have a lot of data, having a very well crafted feature engineering strategy where you create, 10 features or 20 features at most, but they are very relevant. You train a model with a small set of features with the data that you have, and you can have a good model. Okay, so it's a way to inject that expert knowledge, to reduce the data requirements, and to improve results. It will not always work. Obviously, representation learning and deep learning are great. I am a deep learning researcher myself, so I also I work mostly with deep learning, and throughout the years I worked mostly with deep learning. But even with deep learning, what I see in my results personally is that many times feature engineering, particularly when you don't have a lot of data, is very valuable still.
Oh, and the final question, it's by a certain Pedro Prats. And I think this relates with the bonus failure, the wrong problem, the relationship between business and engineering. And the question is from I'm not very savvy in AI, and I reckon that AI engineers get too technical too fast. So people on the business side really need to understand what's happening, and I've seen in your presentation several steps that I've been involved in, like data monitoring, assessing performance, and whatnot. So advisors, well, as a product manager, I'm here, I'm listening carefully, so I'm trying to understand these concepts. But advices for engineers too, what can they do to better communicate with business?
I think that that is a very good question. I think that it is really important to understand what is relevant to the audience that you are engaging with. If you are talking to a product manager, probably the type of model, whether you are using deep learning or random forest or whatnot, it doesn't really matter unless, for example, it changes the engineering constraints, right? Or it changes the kind of product that you can build with that. If there is no impact, probably you should discuss that with your peers, right? You can receive valuable feedback, you can have a meaningful discussion, and you will not be able to have a meaningful discussion with the PM, about your algorithm. The PM will not know if you should use A or B. So you should focus on really what is the implication. Imagine that you find out that A is better. What is the implication of that to your PM? And what is the implication of that to your engineering team? For example, are the latencies different? Are the throughput different? Is your model stateful or is your model stateless? These are the things that your engineering team needs to know, among others, right? What is your pipeline? How about orchestration? These things are things that you need to discuss with your engineering team. With your product, what is your input? What is your output? Right? This is super important. What do you expect? What do you need to make these predictions? And what is the output? Can I trust that output? Sorry, I don't know what random forest means. So the one thing I want to know is whether I can trust the output or not. So these things, input, output, how can you fit that into a product? What kind of value proposition can you build based on the output that you have for your service? Maybe that kind of conversation is what you need to have with your PM. And obviously, it takes a village. To have a good AI service, you need everyone. You need the product manager, you need the AI researcher, you need the engineer, because all of them will know different things, and there is no way that you can build a good product, a good AI product without all of them. Does it answer your question, Pedro? Hopefully so.
Yeah, yeah. I was my question. It answers, but also I hope that all these people here can use this in their careers to advance. And I think that well, this was very helpful to me. I thank you very much, João, and everybody here. There's a lot of people online still, so I thank you all. This will be available offline, so you can rewatch and give it to your friends to watch it. I hope that you have a great evening, rest, and let's do this. Thank you
Bye
very much,
bye. Thank
João.
you all.
Bye. Bye,
It was a
everybody.
pleasure. Bye bye.
Bye.